So good morning, everyone. So okay, this is Sunday today, but okay, due to the weather, I think you prefer not to be on the boat today. So why not be here? Okay. So I will talk about well. You've heard many times during this lecture so far that there is a relationship between TR and integrable systems. I will try to make it more explicit. In fact, let me just recall a little bit of some things that we have seen. So the central notion of in TR is a notion of spectral curve. And to a spectral curve, let me call it S, we associate, S, we associate some sequence omega gn and fg of S. Okay, and they have beautiful properties. And what are they related to? So for example, you have seen that in the Gaetan's lecture yesterday that omega gn can be written as an integral on some space mgn with some class omega, whatever it is. Okay, we have seen you have so very well. This is something we have not done at all during these lectures, but there is a very strong link between TR and so this is TR here. This is a very strong link with random matrices. This is something we have not done at all. What I'm going to talk about today on this example, but it's just to be thought of as an example. We have also the enumeration of maps. This was mostly LBAS lectures. In more generally, enumerative geometry, like for example Hurwitz numbers, but well, this is related to that as well. And so far, we also had the lectures by Nicolas and Olivier about integrable systems. Well, with the notion of quantum curves. There was a little bit of the notion of tau function. But there is much more to say about integrable systems than these two notions. There is another thing that we did not mention too much, is the notion of Cft. And of course, everything is related together. I don't know, for example, Kontsevich used the random matrix model to prove his conjecture. I mean, okay, you have relationships in all ways. There are random matrix models for the enumeration of maps. Okay. There is a relationship between Cft and integrable systems and all that. So, okay. So just to give a picture, but today I want to concentrate more on the bottom part. So both integrable systems and Cft. So let me recall what is. So my first part will be some properties of TR. So the object we start with is the spectral curve, so which is for me the data of a map X that goes from a surface to a base curve. The one form YDX, which is also omega 01, and a one tensor one form, which will be our omega 02. Just to illustrate, if I could draw the plane X, Y, the curve would typically look like, okay, something like that. You have to remember that X and Y are in fact complex, so it's two-dimensional real. I am plotting one dimension versus one dimension because I am not good at plotting two dimensions versus two dimensions. But the curve is in fact a two-dimensional object. Okay? There are special points called the ramification points. There are also some nodal points, possibly, but they are not ramification points. on each point here, each point on the base, let me call it x, has several preimages. Let me label them z1 of x, z2 of x, and up to zr of x. The labeling cannot be defined globally. It's local, so this is valid only in a small set, in a small open set, in a neighborhood, simply connected. All right. So just let me say one thing. What is rescaling a spectral curve? So let lambda belong to C star. What I will call lambda S is simply the curve with the same x, but I multiply y dx by lambda, and I don't change b. So I just rescale y dx, the one form. An important theorem, which is very easy to prove, is that the omega gns are homogeneous with this rescaling. Omega gn of lambda s is simply lambda to the 2 minus 2g minus n omega gn of s. It's almost obvious because the definition of topological recursion, the y dx appears only in the denominator. And when you want to compute omega gn, you apply 2g minus 2 plus n times the operator k, so you get the lambda to the power 1 over 2g minus 2 plus n. It's almost obvious from the definition. But this will be important. Now, from a spectral curve, so I recall that TR associates the omega gns and also the fg's, which are the same as the omega g0. And so far in the lectures, you've never seen how to compute f0 and f1. But okay, maybe I think today you will see f0. I will not give f1, or maybe yes. Okay. So now some definitions. So I will start by defining the partition function. So, and here I introduce a formal, so h bar will be a formal parameter, which means that I don't really want to give a value to h bar. It will just serve as encoding many terms as an expansion in powers of h bar. And basically what we want to make is sum from g equals 0 to infinity of h bar to g minus 2 fg of s. And we'll define the partition function as the exponential of that. So z of s equals that. Okay, leave some space when you write. It seems to be both a function of our spectral curve and a function, at least a series in h bar. But observe that this quantity is the same thing as fg of h minus 1s because of homogeneity. So this will be exponential sum from g equals 0 to infinity. And you see that everything in the end depends only on h minus 1s. Well, this is to be understood as a formal series at large spectral curve. So h bar going to 0 will be what I will call the large spectral curve. And very often I will also call it heavy limit or heavy spectral curve, heavy limit. Okay? Since it's omega 0,3. Okay. It's just to show you that there is a universal expression, a universal combination of theta functions that you normally, so whenever your spectral curve has genus non-zero, you should normally glue all these terms to the partition function to call it a theta function. In fact, this is what Olivier was doing in the lectures. I will not say exactly what they are, sorry. Here, by theta. I will not say much more, but just I will say that this combination of TR functions and theta functions are modular invariants. In fact, what can be proved with TR is that the FGs are almost modular forms, and these completion with theta functions are modular forms.
So these theta functions on what surface? Okay.
On the same sigma, the same sigma we had here.
What do you mean by quasi-modular forms?
Quasi-modular forms, sorry.
Is this the discrete Fourier transform, the same as the discrete Fourier transform?
Yeah, it is, in fact. So you can, so basically the theta function is a Fourier transform of an exponential quadratic. I'm just using that. Okay. So
this is a theta function evaluated on that, so
yes, and I don't want to explain exactly at what, where it is evaluated exactly. I mean, what are the arguments inside the theta function? We can discuss that later.
I mean, when you write theta,
yes.
Sorry?
Okay, theta is
a multiplication.
Theta is a function of two variables.
Okay, okay.
Theta is a function of two things.
Yeah, that's what I want.
It's a vector on the quadratic form, and which you can deduce from the curve, and I will not say what. But
the parenthesis, the big parenthesis, the 1 plus is a factor.
The 1 plus is a factor. It's a multiplication here. Okay, sorry. Yes.
Does this tau function still have some rescaling properties, like the
Yes.
in terms of h bar if you rescale?
Yeah, yes,
okay.
because everything depends only on h bar minus 1 times omega 0,1 everywhere.
But the theta functions also have some h bar.
Yes, also. The theta function also has that property.
Yeah. Okay.
Okay, so to call it the tau function, so basically the difference between the partition function, which I could call the perturbative partition function, and this one is the non-perturbative partition function. So in what Olivier was calling it, the non-perturbative. Now, okay, for the moment, tau function is just a name. To really say that it's a tau function, you have to prove that it obeys the properties that people in integrable system would require to call it a tau function. And that's one of the issues, is to prove that TR, or that every time you have a spectral curve, and every time you compute that guy, it has the properties that are the ones that define a tau function, usually in integrable systems. That's a conjecture for the most general case. It has been proved in some cases, case by case. It's not yet proved in all generality. Okay. Now I will do the same for the. So I will also introduce another notation. So from now on, I will. So now I will consider genus of sigma equals 0 to simplify, but everything that I'm going to say would work for here genus. It's just that in genus 0, I don't have to write all that. So I will spare some time. But think that each time you have genus non-zero, you should make the theta completion of everything I'm going to write. Okay, so another notation I will use for this tau function or partition function, I will use just a bracket like this, V of S. Okay, why not? Just a notation. Yeah, for tau or for z, in genus 0 it's the same. Well, sorry, h bar minus 1s. It is just a notation, and v is just a letter in the alphabet. Later it will, okay. In CFT, we will recognize that it means something. Okay. So let me define the following things. Omega n of z1, zn, and sorry, it depends on our spectral curve. So omega n of h bar minus 1s, and evaluated at z1, zn, is sum from g equals 0 to infinity, again, h bar to be 2g minus 2 plus n, omega gn of z1 of s, z1, zn. Okay, and due to the homogeneity, it's the same thing as sum from g equals 0 to infinity of omega gn of h bar minus 1s, evaluated at z1, zn. Okay, so far, no big thing. Compared to what, for instance, Danilo was explaining on the Hurwitz numbers, these guys are the analog of connected. And Danilo showed that many properties were interesting if you consider also the non-connected. So let me introduce another notation, omega, and I put a black dot like Danilo was doing. H bar minus 1s, z1, zn. Let me start by the first values of n. So omega 1 is just, by my definition, would just be that this is the same thing as omega 1. Okay, let's look at what I would like to define for omega 2. Well, we'll just, so it's h bar minus 1s, z1, z2, plus omega 1 times omega 1. I mean h bar minus 1s, z1, h bar minus 1s, z2. Okay, in fact, and so on. Omega 3 with a dot would be basically the omega 3 connected plus all the possible ways of putting the variables in omega 1 and omega 2 plus all possible ways of putting variables in omega 1, omega 1, omega 1. So here we have 3 terms, in fact. And in general, the formula is the following. Omega n dot of h bar minus 1s z1, zn is the sum of all partitions. Let me write it this way. Mu are partitions of z1, zn. Product from I equals 1 to length of mu, so the number of parts. Omega, the size of the part of h bar minus 1s times and all what you have in the part. Okay? In some sense, you glue all the connected things to get the non-connected ones. So for instance, omega 3 dot is just all the possible ways to put the 3 variables either together or separated in as many components as you like. And regarding the combinatorics of maps of moduli spaces, it just corresponds to having disconnected surfaces. Now I will introduce some notations. I will introduce another notation for this omega n dot of h bar minus 1s z1 zn. I will introduce the following notation. But don't write immediately. I will again use this bracket notation. I will put again my VH-1s. And I will somehow encode the fact that it depends on n variables by inserting n things that I will call j, z1, j of zn. This is just a notation, and don't write it immediately at the moment, because look at this picture here. So let me select several points, x1, x2, up to xn in generic position. Each of them has a certain number of preimages, okay? And in fact, let me choose the point z1 to be one of the preimages of x1. So let's say that z1 was z with some index I1 of x1. Z2, let me choose it as the preimage I2 of x2, and so on. On Zn, let me choose it to be the preimage In of xn. And to record that in the notation, in fact, I will prefer to write that ji1 of x1, jin of xn. And together, and so now you will introduce a kind of notation. J of x will be the vector j1 of x, j2 of x, jr of x. So instead of having a collection of, we're going to call these amplitudes. These brackets, I'm going to call them amplitudes, and it's just another notation for that function. And the fact that we want to label them with preimages is because we want to think of them as multi-valued function on the base, and the labelings just remember in which sheet we were. So here we had something that was really globally defined, and here we lose this information somehow. Okay. And it's because I agree, this is not the best possible notation, but it's usual.
Sorry, could you use another marker?
Okay.
And Bertrand?
Okay.
Above the omega n, it should depend on x1 and xn, right?
Sorry?
Omega n dot, here you write it as function of z1 to zn, and
Yeah.
below the notation is with x1 and xn.
Exactly. So on it's because we have this problem.
Okay.
Well,
You
we made
evaluate
this
it here.
choice. So zi equals, so zj, let's say, is zij of xj, with j equals 1 to n, and I can take, it means that zj is chosen to be one of the preimages of xvx. So indeed, this notation is a little bit misleading. It really corresponds to that. So it's misleading because somehow for each point you have to choose a labeling of the sheets, and somehow you lose the global information. But nevertheless, let me take this notation and let me put them all together in form of a vector. And in fact, I will not put them together in form of a vector. I will put them in form of a vector in a Cartan algebra, and which means a diagonal matrix.
Are you fixing the locations of the punctures? Are you fixing the locations of the punctures, or will you move the x's around?
This is only local. So basically, the labelings of sheets is local, and you have to see if it glues well when you move the points. And indeed, this is an issue. Here, this was not an issue. This is global. And this notation, I agree, is not so well defined. It depends on how you label the sheets in each, above each. So you should decompose the base on open sets on which you have a well-defined labeling, and you want to know if they glue well together when you. So what are the transition functions between the different cards? And it should glue well to make a well-defined globally meromorphic function. at least order by order in H bar. And this is a deep issue, this order by order in H bar. So order by order in H bar, everything is glue well. Does it survive when you take the sum over all powers of H bar? That's a deep issue.
Okay.
But just I want to use this as a notation because this is the Cft notations, usually in Cft. And so, or another way to write that is that j of x will be sum from I equals 1 to r of ji of x ei, where ei is the diagonal matrix 0, 1 in the ith position, and 0 elsewhere, which is an element of the basis of the Cartan algebra of GLR. So this is the Cartan. So J of x belongs to the Cartan algebra H, so the two Cartan of G via the Lie algebra GLR. And remember, this was the sum from I equals 1 to R of Gi of Zi of x Ei. So, well, let me call this H, like that, which is the Cartan of GLR, which just means the set of diagonal matrices of size R.
And R is the degree of the cover?
R is the degree of the cover. Yeah, so it was written here. R equals degree. Okay. Yes. In fact, remember that omega n is a one form in each variable. Omega n is a one form. So if I want the notation to be consistent, not only the j's are going to form a diagonal matrix, but they are going to form a diagonal matrix, which is a one form also. So in fact, it's not really H, it's H tensor one forms. And let me call it K sigma 0, which is the canonical bundle of the base, or in fact, okay. Well, yeah, okay. Let me write it this way, but I'm very loosely about that. Okay. The idea is that at each point, J is a diagonal matrix times times dx. And if they glue together well, it means that you have a bundle valued in the Cartan algebra over your curve. On the Cartan algebra, the set of diagonal matrices is a subspace of the Lie algebra, which is the space of all complex matrices of size R. So in fact, this is somehow a section of in a bundle in the Lie algebra over the curve. Okay, but so for the moment, this is just a notation where I borrow the Cft language just for the notation. And the J's are called the currents. And it is basically the Sugawara notation, which was one of the founding papers of CFTs. So think of the insertion of points in the omega n's as currents in a CFT. And the bracket is going to mean what in CFPT people call amplitude. So you should think as the currents to be some objects, and the bracket means that somehow you have, well, they are somehow operators, and the bracket means that you want to evaluate them as acting on some thing, well, but this is called the fundamental state or the void. Or, okay? And the bracket means somehow integrating something. And it's called amplitude. And to be precise, everything here is holomorphic in the variables. So it's only the holomorphic part of amplitude. This is what people usually call the conformal blocks, and only the holomorphic part of conformal blocks. But I will call that amplitude, even though I really mean, in fact, the holomorphic part of conformal blocks. And if you really want to go to an actual CFT, you have to take both an holomorphic part and an anti-holomorphic part and combine them together in a way that you get something globally defined on the curve and so on. But so, this is just a notation. So now we have our partition function, which I wrote as the amplitude of a V. We have our omega n's that I wrote as an amplitude of some currents. Another thing which was very interesting in the story, basically all the talk by Nicolas and Olivier, was about the wave function, psi, h bar minus 1s, and it depended on the point. So in the, and also in my first lecture, it was defined as exponential sum over g and n, with n larger than 1, h bar to the 2g minus 2 plus n over n factorial, and integral. So in my first talk, I was integrating from infinity to z of omega gn, right? So it depended on the point. It depended on the point z. In fact, it depends on another point, infinity. And in fact, let me replace infinity by another arbitrary point. Let's call it z tilde. And now I will say that this is a function of both z and z tilde. And to recall that that z is the endpoint of the integration and z tilde is the beginning of the integration. So in fact, the line of integration is a segment z tilde z. If you want, this is in fact, it is a Jordan arc that goes from z tilde to z. And it goes from z tilde to z. You could think of it as, so it has boundaries. And the notation for boundaries usually is to call it a divisor. So let me, in fact, to tell the truth, psi is not really a function of z and z tilde, because whenever you integrate a form, you don't get a function. You get something which is multi-valued. You cannot really call it a function. But in fact, it depends really on the path that I will call gamma from z to z tilde. So in fact, psi depends on the choice of path of a Jordan arc. So let us choose a Jordan arc between z tilde and z. And psi is actually a function of this arc. It's an abuse of notation to write it as a function of the endpoints. In fact, if you put the theta terms, it really becomes a function of the endpoints. And in fact, this is the reason why the theta terms were first introduced. But let me skip that question for the moment. In fact, even if you are in genus 0, for instance, omega 01 can have poles. And it matters whether your integration path goes where it goes with respect to poles. I mean, each time you cross a pole, you could pick a residue. So the integration path really matters. And the notation for the boundary of an integration path, the notation for a boundary is just you take the endpoints and give them some weight, +1 for the end, and -1 for the beginning. This is a divisor.
Sorry, this one I don't understand. You said even if we have the genus 0,
Yeah.
so you say the path is important, but then I don't understand that in the language of the CFT in, for example, Sugawara occurrence. Then
That's what I said. Okay. For the moment, think of it as an abuse of notation. Okay. We can discuss that later, and the CFT is just not so well-defined notation, but which makes you have some intuition.
Is the bracket around the Z just notation, or does it indicate that you're taking some equivalence class?
Well, this is the bracket here. No, here this first bracket was just to say a segment. Okay. In fact, I don't really want a segment. We just choose a Jordan arc.
I just meant the second.
Here, the bracket here is the usual notation for the notion of for some notion which is called divisors. So a
it's
divisor.
just notation. Okay.
A divisor is a sum. Okay, let me call it a collection of points, of weighted points. And since it is a collection, in fact, usually we write it as a sum. So let's say you have a collection alpha 1, Z1, alpha 2, Z2, and so on, alpha k, Zk, where Z is a point on your surface, and alpha is a complex number. Alpha I belongs to C, and Zi belongs to your surface. And the notation is D equals sum of alpha I, Zi. And in fact, very often, I will use sum of alpha I, Zi, and I will forget the bracket, because it's long to write. It is a notation very standard in algebraic geometry, for example. It's just a collection of points that have a weight associated to them, and this weight can be, in this example, the boundary of this path will be denoted weight 1 for the arrival of a path, minus 1 for the beginning of a path. Well, you could take integer numbers, but you can also take complex numbers. Just weights on whatever they are. So indeed, in this example, they are integer numbers. They are 1 and minus 1. In general, now you could choose a path. So if you have, let's say, 4 points, Z1, Z2, Z3, Z4, you could choose a Jordan arc going from there, and a Jordan arc going from there, and the sum of those two Jordan arcs, and let's say gamma Z1 to Z2, gamma Z3 to Z4, and what are these arcs important for? They are important to do integration. And let me define. So by definition, the integral over the sum of paths by definition, this is the sum of two integrals. And in general, this will be the primitive. So if you have a differential here, this will be f of Z2 minus f of Z1 plus f of Z4 minus f of Z3. And if you write that the boundary of your gamma, so call this gamma, if the boundary of gamma, according to my notation, is Z2 minus Z1 plus Z4 minus Z3, so you write it as sum of alpha I, Zi from I equals 1 to 4. You see that Z2 has weight plus 1, Z1 has weight minus 1, Z4 has weight plus 1, Z3 has weight minus 1. And by definition, the integral over gamma of df will be sum of alpha I, f of Zi. Well, just to show that the notation is convenient. And in fact, by abuse of notation, we shall write it as an integral of d, meaning that it really depends only on the endpoints. This is not correct. It should really be an integral over the gamma. But I mean, if your form is not an exact form, this is really an integral over gamma, but it's a standard abuse of notation to write it as a function of the endpoints. So I will use this standard abuse of notations, and I will generalize the psi function. In fact, so that's what we've been doing so far using this abuse of notations. We were writing the psi function as a function of z, whereas in fact it was a function of the path. But so, let me now define psi of h bar minus 1 s, d, a divisor. But in fact, I really mean a gamma whose boundary is d. Let me call it gamma d. And it is exponential sum over g. N is larger than 1. H bar to 2g minus 2 plus n over n factorial. Integral over gamma d. Integral over gamma d omega gn. And now let me introduce the Cft notation for that guy. Let me call it product from I equals 1 to k of v alpha I of zi times my vs. H bar minus 1s. Okay. So, and the name for that is Vertex Operator. What? K is the number of points. It's the number of points in the divisor. I take a divisor with k points. What?
Next year at the school, you give a course on CFT. Please! CFT for stupid people like me.
Well, in fact, to really call it a vertex operator, I will do the same trick I did for the J's. I will project on the base. I don't want to write it on the surface upstairs. So it's really defined on the surface. But the use in CFT is to write it as function on the base, and so I have to choose some. So you have to choose some preimages. And in fact, we'll do something. So now let me choose an X here and take the preimages. And in fact, let's choose a divisor with possibly points at every of the preimages. So let's use, so in fact, so X belongs to sigma 0. Let me choose the preimages X minus 1 of X. Let me call it at least locally Z1 of X up to ZR of X. And let me choose a divisor such that it contains Z alpha I, Zi of X. I equals 1 to R. And let me again, as before, make the vector alpha, the diagonal matrix of alpha 1, alpha R. Okay, I should have said something important. The degree of the divisor is the sum of alpha i's, I equals 1 to k. And I will, so the degree of the divisor is the sum of weights. And I will, from now on, only consider divisors of degree 0. I will always assume degree of d equals 0 in all my choices.
Sorry, I just lost your writing. So this integral over WGN and afterwards Z1 to Zn?
Sorry, no, it was the, what remained from the previous
I see, okay. So it goes to the next line. I see,
Yeah.
okay, thank you.
Okay, all this was a remainder, it's just not been erased.
Sorry, in this divisor notation, shouldn't there still be different x's?
Yes, so that's for each x. So here, okay, each x will have a set of preimages. So
Yes, I get that, but the divisor you're writing down seems to only depend on one x. Shouldn't you have alpha I, zi
okay.
of
yes,
xi
right.
or something?
So, okay, so for each now xj, I will call them alpha ij, xj.
Yes, thanks.
So alpha j will be alpha j. Sorry, I should call them alpha j1, ji. So alpha j1, and so on. Alpha jr. And again, it will belong to my Cartan algebra.
Sorry, can I just go back briefly? What is the definition of the capital J's? Because I thought the brackets was like just a notation, so then
The definition of capital J was the diagonal matrix made of all preimages of the projection. So you take a point, so you see the capital J is defined for points on the base.
Right.
So by capital J, you just mean the collection of all the omega n's here evaluated as the different preimages. On each J, so capital J is a diagonal matrix, and in fact, when you just choose one of the entries when you write this, and choosing one of the entries is like choosing one of the preimages, and the value of that. This is just a notation to say that you evaluate omega n as the corresponding preimage. It's just a notation for multi-valued function if you want. So this one is mono-valued on the curve, but it's multi-valued on the base. So you just represent this mono-valued function on the curve as the collection of multi-valued from the base, on the different values corresponding to the different sheets. You encode them as an index. And a way to put all these indices together is make a diagonal matrix. It's just a way to collect them together. And this is not defined globally. This can be defined only in a cart, because the notion of labeling the indices is not defined globally. So this is a notation valid only within a cart, but this is the standard notation. So now, in fact, now what we can define is we have, so now what I will really call the vertex operator, so it was not really that, it was product of alpha, okay, let me call it alpha j with alpha j is a vector in the Cartan matrix, like that. So now it's really called the vertex operator. So a vertex operator is labeled by a point. It's V of a point on the base, on sigma 0, and a weight, which belongs to the Cartan algebra, so a diagonal matrix. And by definition, this means just computing that. So we have several ingredients. We have the vertex operators, we have the currents. And now I will write the Vira-Zoro and W algebra generators. And they also have a natural counterpart in topological recursion. Okay. In fact, if you look at the definition of my omega n's, remember, omega n's was just the summation over h bar of the omega gns. This is singular. Where are the singularities of the omega n's? They can be at the ramification points, but let's not talk about the ramification points for the moment. I will say more about that. They can be singular. The other singularities apart from ramification points are in fact, omega 02 is singular when some zi approaches some zj. Whenever you have some zi close to some zj, you have a singularity. It's a pole. It's a double pole. And in fact, the only place, so remember in omega n we had a sum. because this is the disconnected part, and basically there is always an omega 02 in every omega n somewhere. And so I'm going to talk about OPEs. So omega n dot of h bar minus 1 s z1 zn, it always has the same behavior. Dx, so and let me call zi, let me call x of zi equals xi. So I take the projections. It always behaves like the omega 02, dx1. So let me take the limit where z1 approaches z2. dx1 dx2 over x1 minus x2 to the square. But that's only okay, times. And what remains is just the omega n minus 2 dot of h bar minus 1 s z3 up to zn. In fact, you have this singularity only if it was really coinciding point on the curve upstairs. So which means it's if you have this singularity only if it was the two preimages in the same branch. So if you start to reintroduce the notation here, this means that in the Cft notation, gi1 of x1, ji2 x2 and so on, jin of xn. What is its times v s? It behaves when x1 goes to x2, delta I1, delta I2 over x1 minus x2 to the square, dx1, dx2, ji3, and so on, jin, v, okay. So from every spectral curve, if you construct these amplitudes in this way, you always have these properties, and these are called the operator product expansion, so which is just a way to say how do things behave, what is the singularity when 2 points get close to each other, and what is the limit behavior, and it is always a double pole. And so all things that we construct from TR always have that property of double poles when two currents come together. This delta I1, I2 is in fact a Cartan matrix of the GLR algebra. In general, for more, all this can be generalized to other algebras, and here you would put the Cartan matrix. And this is something, okay. Now, what is a CFT, in fact? What is the definition of CFT? In fact, CFTs have been used by physicists for a long time. There is a lot of things about CFTs, and the idea in physics would be that you have a Hilbert space with some operators. It's a very infinite dimensional Hilbert space, on these operators must satisfy some properties and blah, blah. But in fact, it is not so known if such an Hilbert space actually exists. And there are many constructions from well, let's say perturbative or things like that, but it's not that clear. And in fact, the best way to define a CFT is a set of axioms. Usually these are called the Bootstrap Axioms. And the Bootstrap Axioms are very strong axioms on what these amplitudes, what properties they should satisfy. And one of the properties you want a CFT to satisfy is exactly that one, the OPEs. Well, you have more OPEs that you want to satisfy. Another OPE is what happens when a current is close to a vertex. That's another OPE you want to have. And believe me, the OPEs, so TR, implies the OPEs of CFT. So I just ask you to believe me. This construction satisfies the OPEs of a CFT. So we are on a good way of defining a CFT from TR. So now I want to go to the Virasoro on the W algebra. Yes, the OPE is the set of axioms how the amplitude should behave when points come close to one another. In fact, to have a full set of OPEs, you should not only look at what happens when xi is close to xj, but also when xi is close to a singularity of omega 01, which is done here, and what happens when so if you start defining the psi, you want also to see what happens when some xj is close to another x, and so on. Okay. But believe me, it's satisfied by TR, and it can be an exercise.
Is the other direction of the arrow true?
Of what?
Of that arrow. So if I give you a set of axioms, can you reconstruct the spectral curve?
Good question. Well, no, well, yes or no. You can guess a spectral curve, but in fact, proving that it's computing the same thing is hard, and it's more or less the problem of quantum curves. Well, okay. And in fact, the problem is really on the CFT side. So you have some axioms, and you want to find some quantities that satisfy the axioms. The main problem is that the axioms are over-determining. So every quantity can be computed with the axioms, but not in one way, but in several ways. And the big question is, do all the ways agree? And that's related to the existence of quantum curves, to Hirota equations, or it's called crossing symmetry. And this is a very non-trivial statement. And so you will have, at some point, to check that crossing symmetry is satisfied with your guessed spectral curve.
Okay.
And this is the non-trivial part.
I have two questions. One question, is it possible from TR to prove all axioms of BPZ?
Well, it depends. It has been done in some cases, but not in full generality.
Mm-hmm. And the second question, even more technical, can you recast screening, expression for screenings from TR?
Okay, I'm not so sure what is screening, but I think that it is there, yes.
Thank you.
Yes, I'm almost sure it is. Okay, let me show you where are Virasoro generators, and in fact it is the loop equations in TR. So TR loop equations. And let me remind you what I call loop equations in the case of Airy. In the case of Airy, I was writing the following thing. We took for an arbitrary g on n, we took omega g minus 1 n plus 2. Let me write it this way. Now I shift everything by 1, n by 1 compared to what we are doing. I add here z minus z and z1 up to zn plus sum g1 plus g2 equals g, I1, I2 equals Z1, Zm, omega G1, 1 plus I1, Z I1, omega G2, 1 plus I2, Z I2. Okay. Let me multiply by h bar to the 2g minus 1 minus 2 plus n plus 2 and take a sum over g on n.
Bertrand, shouldn't there be a minus z?
There is a minus z, of course, and it's important for what I'm going to say. Because here, it was in the case where we had the spectral curve with only two sheets, and z was, let's say, square root of x, and minus z was minus square root of x. Sorry, they should be on top of each other. And this is x, which was z square. So this is the special case where we had exactly two preimages. I will rewrite this expression when we will have more sheets. But let's focus on this expression. Let's first do the sum over g on n of that. And when you sum over g on n, and also put the non-connected parts in all possible ways, eventually you will arrive to omega dot n plus 2 of z minus z, z1, zn equals. So here we had the right-hand side. And remember, in the Airy case, what we found is that all this expression was delta g0, delta n0 times x of z. This is what we had found. No, sorry, plus sum from I equals 1 to n d I of 1 over x of z minus x of zi times something. Omega n minus 1. No, omega n of z1, zn. This is what we had found. But the nice thing is that in terms of x of z, this belongs to, and everything was a quadratic differential, so multiply by dx of z to the square. Where was minus, but the nice thing is that this belongs to c of z, c of x, sorry, c of x times dx square, where x is the image of z. Okay. The important property to retain is that this is a very simple rational fraction of x of z. Well, the theorem is that it has no pole at ramification points, but moreover, it was equal to this expression. And if you think of it, this is the only rational fraction of x which satisfies VOPs. So just knowing that it has no other poles than the ones given by the OPEs tell you what should be the right-hand side. So the actual theorem would be that this quantity, this precise combination, has only the poles dictated by the OPs. It's analytic outside of the poles dictated by the OPs, and very often the notation, okay, no, I will tell you the Cft notation for that in a moment, but so basically what we found is that, so let me introduce the notation. Well, no, first let me generalize to the case where we have more sheets. So here this one, the z, if you want this one, the z1 of x, this was the z2 of x, and if you have more sheets, you would have z3 of x and so on. And in fact, what I should do is replace the z and minus z by sum from I equals 1, I smaller than j, between 1 and r, of zi of x, zj of x, okay, and same thing here, replaced by zi of x, And if you replace this one by zj of x. Okay? And in general, let me define, so define what I will call wk of x, j of z1, j of zn, and v h bar minus 1s. And I recall that a point on the curve is equivalent to a point on the base plus a label, okay, in the Cft notation. So the point on the curve is the data of a point on the base curve and the label. So it means which j we should choose. But so this is more concise, so let me write it this way. By definition, is equal to sum over I1 ik between 1 and r of j z I1 of x, j z ik ir of x times j of z1, j of zn, v h bar minus 1s. Or if you want, wk of x is the sum over I1 ik, j of z I1 of x, j of z ik of x. These precise combinations, so if you rewrite it as element of your Cartan algebra, this precise combination of elements in the Cartan algebra is called a Casimir. And it is invariant order changes of basis. I mean, it has nice properties. And so these are the Casimirs of H of your Lie algebra. So here, which is GLR. Times dx to the power k. So it's a case order form times the Casimir. And the property is that, and so the theorem which you can prove from topological recursion is that, so the theorem from TR is that wk of x times anything in an amplitude has poles. Belongs to c of x dx to the k, and poles only where OPE allows. So basically coinciding points on points that are poles of the spectral curve, poles of ydx.
Can I ask you why only GL2 in a sense? So where is the GL2 coming from?
Or GLR, so it's GLR.
GLR, okay,
R is the number of sheets.
Okay, GLR.
The reason is because choose, so an example, choose now, take a matrix that I will call phi of x, which belongs, it's a matrix, R by R matrix. And in fact, in general, you would like to choose it to be the representation of some Lie algebra, of an element of a Lie algebra. So in fact, GLR, so R by R matrix is via Lie algebra or GLR. But if you want to take more, to have more constraints, some symmetries and so on, take now as spectral curve the equation determinant of y minus phi of x equals 0 in some representation rho, and take that as your spectral curve. Then you can rerun the same thing, and for instance, for the here you find the Cartan matrix, and here you would find the Casimirs of your Lie algebra. In fact, it works for Kac-Moody algebras.
Suppose I change my algebra. So say I take, I don't know, GL loop algebra, for example. I can still define that spectral curve. It will carry some parameter.
Yeah.
Will I still find some Casimir then in the same way?
For the moment, I define then pointwise, so for a given x or in a given card, so yes. Okay, so this is, so physicists say that WK is meromorphic. And very often they write it as d bar WK equals 0. And this is called the Ward identities. So basically, the TR automatically implies the OPs on the Ward identities. So you are really in a good way. So the Ward identities are also some axioms of conformal field theories. So TR automatically gives you OPs on Ward identities. And I remind you, the OPs just come from the omega 02, in fact, on omega 01. Everything in the OP is contained just in omega 02 and omega 01. On the Ward identities is really where TR intervenes, because the fact that this combination has no poles at ramification points is really TR, is really what TR is. TR is exactly the condition that there is no other pole than these ones. This is exactly what TR is. So TR is exactly giving you the Ward identities, and you would not get the Ward identities if the omega GNs would not be related by TR. So in some sense, Ward identities are equivalent to TR. And by the way, when k equals 2, the W2 generator is called the Virasoro. Sorry, it's called the stress energy tensor. W2 equals stress energy tensor. In fact, up to a factor -1/2, I think. Yes. Yes. Okay. And so it's a combination of currents, which is really yes, what Sugawara did. Okay. So what time is it? 12:25. Okay. So now I will move more towards integrable systems. So far I was considering only one spectral curve, and just to finish with CFT. So I said TR automatically gives the axioms of OPEs and Ward identities, but the third axiom of CFT, which is called crossing symmetry, is not, I've not said yet what it is, and it is somehow related to the fact that that for defining the vertex operator, things depend on which path you integrate. So in fact, the vertex operator was not well defined. And when you compute these amplitudes, they do not depend, they are not only functions of your point, they are functions of how you computed, and this is bad for a CFT. A CFT should really be a function of points. And so if you want to really have a CFT, this should not depend on how you choose your integration path. And that's the hard part. And another way to rephrase it is related to integrable systems. And it's related to what's called Fay identities or Hirota equations and many things like that. And now I will talk about integrable systems. On integrable systems, so part 2, integrable system. Have to do with deformations. And a large part of what I'm going to show you is that TR gives you solution to Miwa-Jimbo equations for the tau function. So for those who know integrable systems, Miwa-Jimbo is really one of the properties that allow something to be called the tau function. So far I was having one spectral curve. Now what happens when we do when we have a family of spectral curves? So let's consider families of spectral curves. So instead of having one spectral curve, I want to have a family ST with a time. T equals a time. I can also have multi-dimensional times, and in general, I could consider the moduli space of spectral curves. And locally parametrized by, well, let me call that T equals times, now with an S. Well, this will just be kind of local parameters to parameterize a set of curves, a set of spectral curves, whatever that is. This moduli space is something enormous. It's very it's very infinitely dimensional, because omega 01 is a one form which can have poles wherever you want of arbitrary degrees, and we have even seen cases where it's not only having poles, but for example, there was the function sine of square root of x in the first example. We had the Lambert function. All these functions are not even algebraic. They have essential singularities. So you can put really a lot of things in it. The good language is the language of categories. So spectral curves are just objects. Basically, there is no ensemble of spectral curves, but each time I give you something, you know if it is an object in the category of spectral curves. There is notion of morphism. So what we call usually moduli space is modulo isomorphisms. And isomorphisms are basically the fact that everything should be independent by reparametrization of the zi's. So changing, if you call zi or 1 over zi or minus zi, should be, everything should be invariant. Okay. One of the properties we had, so let me recall some example. Let me start with an example. So example, which is more or less the same that Gaetan was also considering yesterday. X equals z squared, and y is, so I have slightly different notation. 1 minus sum from k equals 3 to, let's take a maximum degree d, tk plus tk, z index k minus 2. Z to the power k minus 2. And B is dz1, dz2 over z1 minus z2 to the square, and sigma is cp1. Okay. If the degree is finite, it's easy to see that y squared is a polynomial of x. Y squared, sorry. There is an algebraic relation of degree 2. If there is no even part, y squared is a polynomial of x. But if there is an even part, you need to add a linear term in y. Okay. Okay. Let's take this example. So there are times, and it was in my first sequence of exercises well, but it's obvious here. D over dtk. Well, let me first remark the following thing. Tk is the same thing as the residue at infinity of x to the minus k over 2, yes, x to minus k over 2 y dx. So how can you see that? Indeed, this residue at infinity of x to the minus k over 2 means z to the power minus k. And so z minus 1/2 sum from j equals 3 to d of tj z to the j minus 2, and dx is times 2z dz. Well, that's for k, okay, minus delta k2. For k, sorry, minus delta k3 in the case where k equals 3. And so, I mean, it's just a simple, so the residue just extract the coefficient of z to the minus 1, so you should have j minus 2 plus 1 minus k equals minus 1, and basically it extracts the term k, j equals k. There is a 2 that compensates the minus, the 1/2, and the minus sign is due to the fact that the residue at infinity is not the coefficient of 1 over z, but the coefficient of minus 1 over z. And it's because the local variable at infinity should be 1 over z instead of z. Okay. So this agrees. So the tk's are just the coefficient of expansion of y dx, like that. Now, what is dy over dtk? And leave some space here, because I will multiply by dx. It's minus 1/2 of z to the k minus 2. But if I multiply by dx, so I multiply by 2z dz, it is minus z to the k minus 1 dz, which is minus 1 over k times the differential of zk. Well, now we use the Cauchy residue formula to recognize that this is 1 over k. Residue when z prime goes to z of dz, well, okay. I could have gone, okay, I'm going directly from the first line to the third line. So I put the dz in front, dz, and I don't put the k, minus dz, no, sorry, dz over k, residue 1 over z minus z prime to the square, dz prime, z prime to the k. Do you agree? If you do the Taylor expansion of 1 over z minus z prime to the square, the k coefficient, so the z prime to the minus k, well, I mean, taking a residue with a double pole extracts the derivative. It's as simple as that. And now let me use the fact that the sum of residues is 0 and the only other pole is at z equals 0. So we find that dy over dtk dx is 1 over k, residue at z prime goes to now infinity of z prime to the k, b of zz prime. Okay. So, and I showed you, so in TR, property of TR, the property of TR is that for every g on n, d over dtk of omega gn of Z1 Zn was then equal to, and in fact you take the same, so if you want, this can be written as d omega 01 dtk equals 1 over k residue z prime goes to infinity of omega 02 of zz prime. So a property of TR is that it propagates all the way to all g on n. So this is 1 over k residue at z prime goes to infinity of omega gn plus 1 of z1 zn z prime. For short, I will write that d over dtk omega gn is this operation, and I will give a name to this operation that acts linearly on one of the factors of omega gns. I will give a name in a moment, but for now, let me write it. Z prime goes to infinity of, sorry, I forgot the z prime to the k, of course. Omega gn plus 1. On z prime to the k, let me also call it x of z prime to the power k over 2. Okay, that looks bizarre to do that, but in case the function x would depend in self at the time, you want, in fact, you need that the linear operation you are performing does not depend on the times at fixed x, so that it really lives on the base. That will be important. So that's how you should write things. So let me define...
sorry, Bertrand. You say this is a property of TR, but how are the TK defined for general things?
This was for the example, for this example. In general, I will say in a moment what it is.
Okay, sure, thanks.
This is my goal. How much time? Okay, so I will not have time to go very far, but the idea is the following. So define some linear operations acting on our omega g ends. So basically, which are forms, which are differential forms, but remember they are like product of one forms, and in fact, each time they act on only one of the factors. So which are forms like that, so meaning it's a product of n, it's n times, so it's a one form whose coefficient is a one form in another variable and so on, and each time we shall act in only one of the factors. And let's call it the last one because they are symmetric anyways. So here, let me give a name to those guys. Let me give a name. A infinity k is by definition, it's a, so linear operations acting on forms are elements, so basically they are elements of a dual, they are linear forms on one forms. So the objects I will be going to consider are elements of a dual of the space of meromorphic one forms. So let me give a name. Let me give some name. M1 of sigma is the space of meromorphic one forms on sigma, and I will have to consider its dual. Well, first, the space of all possible meromorphic one forms on sigma is something enormous. It's infinite dimensional because you can have poles everywhere with every degree, and the dual is something very nasty, very horrible. And I'm talking about the topology, sorry, not the topological, the algebraic dual. It is something extremely nasty. Putting a topology on it is a nightmare. I will not go on that, but I will in fact restrict this dual to only certain types of objects. In fact, I will consider only a subset of the dual. And in fact, I will not define it this way. I will just construct it, define it in a constructive way. So let me define A infinity k, so belonging to this dual, is the element which, so basically to define it, I just need to say what it does when I apply it to a one form. And it will be defined as follows: A infinity k applied to a one form, but usually instead of this, it is written as pairing. So the usual notation for dual, for things in the dual, is to write it as a pairing. Is, by definition, is the residue at infinity of x to the power minus k over 2 times omega, and let me multiply by 2 pi I. Yeah.
It depends on the choice of square roots for x.
Okay. Indeed, it depends on the choice of square roots, and you should really think of it in the. Okay. Okay, I will.
So you want to fix it for what?
Okay, if you want, you have plus minus. Okay. Okay. I will say more general definitions in a moment, but this one is, well, it's really for applying to that case, and you should replace x to minus k over 2 by z minus k. This is the choice of square roots. And I will define another one that is b infinity k applied to omega. It will be 1 over k residue at infinity of x to the power plus k over 2 omega. Notice one thing: x to the power minus k over 2 vanishes at infinity, whereas x to the power plus k over 2 has a pole at infinity. And so this one is defined for k strictly larger than 0, whereas the A, and in fact, I use this notation A and B because it's similar to A and B cycles, and I will call them generalized cycles, and they are like the A and B cycles on a curve, but a little bit generalized. And if you think of them, they will be also related to the Darboux coordinates, the Q and the P's, but in a moment. So I think it's time to finish now, and we'll continue this afternoon. Okay, I don't have time to say much more, but okay, I will just say that the TKs were the A infinity k applied to y dx divided by 2 pi I. You may wonder why here I multiply by 2 pi I and I redivide afterwards. Well, it's precisely because I want it to be consistent with the usual notion of A cycles. And in particular, because k equals 0 with this notation is simply just a circle around infinity without a prefactor 1 over 2 pi I, because residues have a factor 1 over 2 pi I, and I don't want it. I really want a circle. And d over dtk of omega 0, 1, you can check that this is the B cycle applied on omega 0, 2, and in general, sorry, d over dtk of omega gn will be the B cycle applied to omega gn plus 1.
So the first question is.
So that's enough for this moment. Oh,
but
are you sure? Okay. Okay.
So the first equation is a definition, and the second is a property?
The first equation, in fact, it is also a property. The definition of TK was that one.
So we are still in the example of the Airy curve?
Yes, we are still in the example of the Airy curve.
Okay.
But now the idea is that I want to make it general for every curve. And in fact, I will call it T infinity K. And for now, the idea is that for more general curves, omega 0, 1 can have poles. So y here, in fact, here, y had a pole only at infinity. And that's why only the times at infinity mattered. In general, y can have more poles, and you should take a collection of times for every pole. And also, what Nicolas explained the other day is that knowing the behavior, somehow knowing the behavior near the poles, and somehow this is what we are computing. We are computing the coefficient of the Laurent expansion near the poles. If you know the behavior near the poles of ydx, it's not enough to really have all the information about ydx because you miss the information about non-contractible circles. You miss that information. So you should supplement that information with other times that correspond to those acycle integrals. And we shall also call them times, and they can also be computed as some linear action on ydx, basically just the acycle integrals of ydx. It's also a linear action. And so basically all the parameters we need can all be encoded in this way, and that's what I'm going to do now. So now, more general curves. So let me, so for the moment, choose let sigma of some genus. Let me call it G hat, because this is the genus of sigma, and it has nothing to do with the G's in the omega GNs, which were related to some integrals on MGN. It has nothing to do. This one is totally fixed. So for example, for Airy, you have the G hat is 0, whereas you can have omega GNs for every G. So it's just because sometimes people are confused about that. There are two notions of genus. There is the G in omega GN refers to counting surfaces of genus G, but it has nothing to do with the genus of a spectral curve. Okay. Let sigma have some genus G hat, and let X and Y meromorphic on sigma. So basically, I do not want to consider the kinds of sign of square root of X or the Lambert function or things like that for the moment. I will later, but not now. So sigma is compact of some genus. So how can we collect all the information? So how can we parameterize these curves? And one way is to take all the poles, so consider all poles of y or x, by the way, and in particular the poles of y dx. Let me call that P, equals that set of poles. At each P, in P, we shall associate a local coordinate, the canonical, let me call it the canonical local coordinate. Okay, I should rather say the projection, the X image of the poles. So I will really consider that the poles are somewhere here. So for Airy, the only pole was at infinity. And I will choose some of the pre-images, and that corresponds to gate on questions. In the Airy case, it means choosing one branch of a square root. But so, so let P belongs to P, and let's call Pi belongs to X minus 1 of P. Of P, with I equals 1, 2, and let me call it L of Pi, because the number of pre-images might not be equal to the number of sheets if some points are ramified. And let me define the local coordinate x psi pi of a point z. Is by definition x of z minus x of pi to the power 1 over order at pi of x, of the function x, if so this is if the order is positive and psi of pi of z equals x of z to the power 1 over the order pi of x if the order is negative. So for most, for generic points, the order equals 1 on psi p of z, if p is a generic point. Okay, let's q of z would be just x of z minus x of q. And in our example, so at infinity, x has a double pole at infinity, so order at infinity was -2. So we take psi was x to the power -1/2, so 1 over square root of x. And if it's ramified, indeed, you have you should take into account the various. You should multiply by the possible square root, roots of unity at infinity. I mean, okay. Let me not erase that one. And now let me define the times tpk of our ydx is defined. This is defined as 1 over, sorry, at residue at p of psi p to the power, so let me call it pi to the power k times ydx. And so by definition, it means that ydx behaves when evaluated at the point z. When z approaches pi, it behaves like sum from k equals 0 to degree of ydx at pi plus 1 t pi k psi pi to the k minus 1 d psi pi plus holomorphic at pi. So, by the way, these local coordinates are only in neighborhoods of pi. They are defined in the neighborhood of pi. So, near pi. They are not global coordinates in general. Well, the Airy curve was somehow accidental. 1 over square root of x was z, which was a global coordinate, but it's an accident. It never happens. I mean, no, it happens. Here? No.
From 0 to degree of ydx -1?
Yes, you're right. I knew you have to shift by 1, but I didn't remember in which order. Indeed, k plus 1 now is equal to a degree. Okay. That's right. So basically, these times contain all the information about the behavior at poles. Very often, I call them kp times. And they are nearly local coordinates, but we don't have yet all the information. Let's also choose, imagine that our surface has units g hat, and so we have some p, so we have some pi's, p1, p2, and so on, p3, and so on. We have some poles, but moreover, the surface has non-contractible cycles, and let's choose some basis of non-contractible cycles, and in fact, I will replace cycles by Jordan arcs. Okay, so let me choose some Jordan arcs, and so A1, A2, and B1, B2. How you choose them is completely arbitrary. You have many ways of choosing such non-contractible cycles, non-contractible Jordan arcs, and it matters whether they go right or left of some, I mean, it matters where they go through exactly compared to the poles. You should avoid the poles, but apart from that, you should really make a choice of Jordan arcs. So AI, BI, Jordan arcs. And let me assume that they form a symplectic basis with respect to intersection, which means that when you, there is an orientation. When you follow A cycle and cross the B cycle, if you follow the A cycle in this direction, or okay, let's say the A cycle in this direction, the B cycle should go upward, not downward at the intersection. And that's when the intersection is +1. If it goes the other way, you say that the intersection is -1. Okay, and let me also introduce the time Ti for I equals 1 to the genus to be 1 over 2 pi I of integral over AI of y dx. So you see it's also a linear operation acting on y dx. It's also an element of the dual space of one forms consisting in integrating omega 01 on the A cycle. So basically it takes the same form as what we had here. And the theorem that you can prove in topological recursion is that the derivatives will be the B cycles integral. That's a fact in topological recursion. The omega gn over these dti's are the B cycles integral. So far in the lectures, we almost never consider higher genus curves, but this is a result that you have as well. And this is why I want to take a kind of uniform notation. So you have some times associated to the poles, and they are associated to some A cycles. You have some B cycles corresponding to them. And also for the non-contractible cycles, you have some times associated to them, and they correspond to A cycles, and the derivatives are the B cycles. So it's kind of, I want to somehow uniformize the notation to take everything together with the same notation. Now, just one remark. I call them times, and you can think of them as parameters for your curve, but in fact, first thing, they are not independent. And for example, when k equals 0, this is just the residue. And the sum of all residues is 0. So the sum of all TPKs is zeros, which means that not all of them are independent. How much time? I think it's finished now. So, remark, not independent. Because sum over all the points of TP0 must be 0. This is one relation, but you might have other relations if you have some curves that have some symmetries. If you require your curves to have some symmetries, you have other relations. Okay, I will stop for now, but let me just give you an idea of what we will. So I will define the A and B cycles as linear operation acting on one forms. There is a subtlety in doing that, and it's precisely why I choose Jordan arcs and not cycles. And we'll see that this property of the derivative being that is true for all sorts of times. But since they are not independent, the good way to write that is to write this, in fact, as a connection on the moduli space. And we'll have to see that this connection is flat. And this is where integrable systems start to arrive. And we will have Miwa-Jimbo equation for the tau function. So that's the next part.
Are there any known examples that has relation between KP times and acycle integrals?
Well, in all the cases I know, the KP times are really associated to the poles. Well, no, okay, you will see a big difference. Some of the times will be called isomonodromic, and some will be monodromies. Basically, some of the times, and in particular, the acycle integrals are, almost by definition, they are the monodromies of YDX. They are not isomonodromic. And when you think about KP times, you really think about isomonodromic times. And these are only those corresponding to what I will call the second kind cycles. Typically, those residues at infinity are second kind, are isomonodromic times. But the residue, so the TP0, so for k equals 0, again, it is a monodromy. Okay. So only the TPK with k strictly larger than 0 can really be called the KP.
Okay. Thank you.
So with Rainier and Danilo, we studied this spin version of Hurwitz numbers. And what we found is an omega 02, which is somehow not allowed. It has double poles along the diagonal and the anti-diagonal. So in your Cft notation, is this related to Lie algebra that is not GL?
Yes, exactly. That's what I said. But so far, I'm concentrating on the GLR, for which the Cartan matrix allows poles only really on the diagonal. But for instance, for the B or C algebra, you can have exactly the type of poles you have. And it would be really nice now to match what you do with this general formalism with arbitrary algebras.
And from the integrable system point of view, can you see like a different integrable systems like BKP or something like this?
Yes, that's what it's supposed to be.
Thanks.